Welcome to The Bee's Knees. I'm your host, JC Meyer. The Bee's Knees is a podcast wild about native bees. Wild and native bees are under threat worldwide. In each episode, we look at actionable things we can do to support these adorable little guys whose pollination work is crucial for maintaining biodiversity. Thanks for being here. Bees are essential in pollinating the crops we rely on, but the continual allowance of insecticides and their effects on pollinators is alarming. The effects of one pesticide, neonicotinoids, is well established, and the use of them is banned in the European Union, but unfortunately not everywhere. The pesticide plot thickens, though, beyond neonicotinoids. Today we're looking at how our gorgeous bumblebees, in their daily foraging, are collecting pollen that's laced with a cocktail of pesticides. What are the consequences of this exposure on their colonies? This is what we're discussing with Dr. Charlie Nicholson, a community and landscape ecologist at the University of Lund in Sweden. He recently participated in an extensive EU-wide bee observation project that found despite tightened pesticide regulations, bees are still feeling the negative effects. I asked Charlie to start us off with a brief look at the effects of neonicotinoids on wild bee species, other pesticides in use across the EU, and what their restriction levels are.
Right. I mean, I think most people have heard about neonicotinoids or neonics, and certainly listeners of this podcast, folks who probably care a bit about bees, right? And neonics were these pesticides developed by Bayer and Shell scientists in the 80s. And they kind of quickly rose to global prominence, in part because they just had a lion's share of the market. I mean, 25% of all pesticides in the early 2000s. And that kind of lion's share coincided with these observations that bees just aren't doing too well. And, leave it to folks to kind of put two and two together and say, well, maybe it's those neonics. And there was this like profusion of research showing these negative effects of neonicotinoids, resulting in some places in the world, like you mentioned, in the EU, for those compounds to be banned or at least largely regulated. But first, it's not true that neonics are banned everywhere in the world. And then second, neonics are only one kind of pesticide, right? There's many other kinds of insecticides like organochlorines, carbamates, pyrethroids, organophosphates. These are all things that can potentially harm bees, right? But it's important to remember that, even within neonics, they vary in their toxicity, right? And this is true for many pesticides. Some are more toxic than others. And this is even also true for insecticides. So we can't really make blanket statements that say all insecticides kill bees, right? It depends on how toxic they are and how much those bees get. This is this kind of classic tenet of ecotoxicology that the dose makes the poison. Yeah. And so in terms of kind of the status of neonics, they're banned in the EU for the most part. There are some like emergency exemptions on their use. But like I said, that's not true everywhere. So for example, in the US, of the almost 1 billion pounds of pesticides applied, about 30% of that contain compounds that are banned in the EU, right? So although we might be making progress in some parts of the world, there's still places where we have a long way to go in terms of understanding what these pesticides can do and incorporating that understanding into an effective regulatory process.
So there appears to be a gap in field-based evidence regarding the impact of landscape pesticide exposure on wild bees. Why do you think this gap exists, and how critical is it to fill?
Yeah, that's a great question. Well, let's just start with some basics, right? All pesticides used in agriculture need to pass through a risk assessment before they're registered and sold. And this includes tests on many organisms, including honeybees, right? But we keep seeing these negative effects on bees of these approved pesticides, right? Once they're registered and once they're sold, growers go out and use them, and then, we see bees dying. So what's up with that, right? Well, I think there's a couple of things, and myself and others see a few important inadequacies in current risk assessment. First is that there's this over-reliance on short-term laboratory-based mortality testing. So short-term as in less than a few days, And this is potentially a problem because pollinators in kind of the real world can experience pesticides for much longer. And we know that toxicity can increase with the duration of exposure. A second thing is that these tests are designed to determine median lethal doses, right? These LD50 values, right? And that's the result that results in the mortality of half the test population. And so by design, these tests don't test for these sublethal effects that we're seeing all the time, right? So these include things on bee physiology, like decreased sperm count, or behavior, like impaired flight performance. And so these sublethal effects in the long run are really going to impact our pollinator populations. But currently, these sublethal effects are not part of standard testing. Third, these tests typically rely on the Western honeybee as a model pollinator species. And as listeners of this podcast probably know, the honeybee is kind of a weird bee, right? When compared to the other 20,000 species. It's incredibly social, forming these massive colonies, and it has relatively advanced, for an insect, communication abilities. And so we've pointed out in another paper that these traits of a honeybee, which are pretty different than the many solitary non-social bees, these honeybee traits are really going to kind of affect how they experience pesticides. So let's recap, right? Current pesticide tests are mainly focused in the lab with short-term exposures. They really focus on mortality testing and not sublethal effects. And they use mostly the Western honeybee as a model organism. I think there's two more important things. And these last bits are actually really crucial, something that we hope our recent paper addresses. And so these tests and most pollinator research to date have focused on single compounds, right? And this is just a practical necessity when working in the lab, as it would be just impossible to factorially test every single combination of pesticide with each other, right? To create every single pesticide cocktail out there. But it's nonetheless relatively not representative of reality, right? Because we know through field monitoring that bees are encountering multiple pesticides at once. So in our study, a pollen sample typically had 8 compounds. But I know of other studies, for example, in the US, in New York apple, pollen samples had on average 17 compounds. And another study in blueberry in Michigan, I think, where pollen samples had about 18 different pesticides on average. So, right, bees are experiencing multiple compounds when they're foraging in the field, but also sometimes these pesticides are mixed together in kind of co-formulations before they're sprayed. Right, so these current tests are not really set up to find effects of this co-exposure or multiple ingredient formulations. And then last, and I would argue perhaps most critically, is that we don't test exposure well. We really just don't assess exposure that well. Right, these laboratory tests are designed to evaluate toxicity, but a thing that our group here at Lund University really is pushing forward is that this risk of pesticides to bees must include not only the toxicity, but the exposure. And examining exposure and understanding exposure of pesticides is the focus of a lot of my research. And as an ecologist, it's really kind of exciting because it's where bee biology and landscape ecology kind of intersect. So I'm just going to take a little bit and talk about that. For bees, exposure happens when their foraging activity intersects with where pesticides occur in the landscape. And where pesticides occur, that's one thing, and that's influenced by agricultural practices and grower decisions, as well as the chemical properties of a pesticide, right? Their decay rates can influence how much of a pesticide a bee might encounter. But where bees intersect with pesticides is influenced by bee traits, right? So let's just walk through a couple of examples of some bees. So there's these bees, Peponapsis, which are these squash bees. They're really cool. And they nest underground and oftentimes in the crop field, right? In the pumpkin field or in the butternut squash field. And so their exposure occurs at their nesting site, right? Because they're living in the crop field and may happen through pollen collected from that squash plant or also potentially from the soil. Right? So the traits of squash bees, nesting underground and being kind of a crop specialist, really influence their exposure routes. Let's compare this squash bee to a small solitary osmia. Right? These are these mason bees. And these small bees correspondingly small foraging ranges. And so their exposure to pesticides may be strongly influenced simply by their proximity to a crop field. So if their small exposure range overlaps with a lot of agricultural landscape, we might expect a lot of exposure to pesticides for these bees. Let's compare this to honeybees, which, as I kind of mentioned before, is a pretty strange bee. And another thing about honeybees is that they have relatively large foraging ranges, able to fly up to about 2 kilometers. And so this means that they could access many potentially uncontaminated patches at a landscape scale and effectively diluting colony level exposure through uncontaminated pollen or nectar. Right, so these bee traits really kind of only play out in the real world, right? And it's critical, right? Exposure, realistic exposure, needs to be assessed in the real world. And so after pesticides are approved, there's currently no requirement for these sort of real world exposure data to be obtained. And so there's no way to assess if our toxic tests combined with exposure predictions are actually reflective of what bees experience in the field. So what our research did is effectively a post-approval monitoring study conducted by independent researchers rather than the regulatory agencies or the pesticide producers, who could also do this type of work. I think it's an important point. And I think it's critical to fill this gap, that we do these kind of real-world exposure tests, this post-approval monitoring. And thankfully, there's some action around including this type of monitoring in the regulatory process. And I want to be super clear in that we're not saying that post-approval monitoring should replace these pre-approval toxicity tests, right? Our post-approval research really depends on knowing what the toxicity of these compounds are, right? So really depends on these laboratory tests, right? So we absolutely need both pre-approval tests, but I think if we combine that with post-approval monitoring, we can really take a step forward in how this regulatory process goes, right? So this post-approval monitoring will help save non-target organism lives and money, right? We can step off a pesticide regulatory treadmill wherein compounds are approved, they're used, farmers get used to them, they like them, and then they're banned. And now pesticide companies have to come back and develop something else, market it, get it through the regulatory process, and get farmers to use it again, right? So if we could actually step off that regulatory treadmill, we could have a much more effective and economically efficient process. And I think one thing that we can all agree on, right, is that this is an attempt to fix a problem beforehand rather than to fix it after the fact. And we think post-approval monitoring is a step in the right direction towards helping us get ahead of the problem.
Are there any other changes or improvements you would recommend to ensure a more protective regulatory process?
Another part of our study that's important is that we didn't use the Western honeybee. We used a bumblebee species, Bombus terrestris. And we think this species is actually potentially really useful because it's sort of intermediate between honeybees, which are a kind of model organism for ecotoxicology, and many other bee taxa, which have smaller foraging ranges, are slightly less social, and don't necessarily have the advanced communication capacities that honeybees have. But that's not to say that we should only use bumblebees and honeybees. Another part of the project that we're on, this POSH bee project, is kind of looking at multiple stressors in multiple bees. And this is actually getting rolled out into an even larger project, POSH bee focused on 3 bee species. And there's now currently work that's going to kind of look at potentially 10 model bee species for environmental assessment.
We were talking earlier about the sublethal effects pesticides can have on bees. Things like total colony production, maximum colony weight, and the number of new queens. What are the real-world implications of these findings for bee conservation?
Yeah, that's an important question. I think in answering, I'm going to touch on two important directions for future research. But again, let's just start with some basics, right? For a population to persist, it needs to reproduce. And for bumblebees and other bees, this means producing new males and queens. And this stage of the bumblebee colony cycle, right, the stage where they produce reproductives, males and queens, tends to happen towards the end of the colony's life cycle. This is an important point to understand because in our project, for other reasons, it was designed so that these bumblebees were only out for crop bloom. After crop bloom, the colonies were brought into the lab. But what that meant is that these colonies couldn't complete their kind of full life cycle, right? They couldn't necessarily go all the way out to the end of queen and male production. So that this meant that these colonies couldn't complete that cycle. They couldn't go all the way out to the end of queen and male production, right? But nonetheless, in our study, we do see that pesticide exposure had an effect on queen production. It just wasn't very strong, probably because of this limitation, right? That we took colonies in after crop bloom, and these colonies couldn't complete their life cycle. We would also likely suspect an effect on queen production nonetheless, because the number of queens a colony produces tends to be strongly correlated with colony weight, which we clearly did see an effect on. That colony weight change declined in landscapes with greater pesticide risk. But I think there's nonetheless a really important opportunity to repeat our study, but get really good queen data by letting colonies complete their life cycle. And this data would kind of conclusively show a strong population level effect of these pesticides. Our study certainly points in that direction, but I think we could have much more conclusive evidence, and it wouldn't be that hard to do. I think the other important implication of our results for conservation is that the effect of pesticide exposure on pollination services is currently not really well understood, right? We see a reduction in the kind of total production of individuals, and we might expect that would mean fewer bees like leaving the colony to make foraging trips, which would mean potentially fewer visits to crop flowers, which might result in larger yield gaps, right? But you heard me say might, right? We don't really know. And as an ecologist well-versed in kind of the concept of ecosystem services, I make sure to distinguish between the supply of a service. So for example, with pollination, that would be the number of visits by bees. And I distinguish that supply with the benefit of a service, right? So for pollination, this would be that, yields are better when bees are present. But I don't think anyone has done a really good job testing whether there are effects of real-world pesticide exposure on bees that in turn influences both the supply, right, their visitation rate, and tests whether or not that creates an effect on the benefit, an effect on yields or yield improvements from pollination. So I think that's another really important direction in future research.
So where would you like to see pesticide-related research go next?
I think a really important direction for the research is this post-approval monitoring. And so we're currently working with colleagues, scientists, as well as folks at these regulatory agencies to kind of start to discuss what that might look like, right? And it's not a totally new concept, right? We're not like reinventing the wheel here. Post-approval monitoring exists in other aspects of society, right? So the classic example is with drug regulations, right? In pharmacology, right? And so there you have this concept of pharmacological vigilance, where, these drugs go through these proof-of-approval tests similar to pesticides. They're approved for use, they're sold, they're used, but their effect continues to be monitored, right? There's this post-approval monitoring. And this kind of pharmacological vigilance, this post-approval monitoring of drugs, has saved the pharmaceutical industry millions of dollars in preventing lawsuits that result from adverse effects that happen after these compounds or these drugs are approved, right? Risk assessment is not perfect. Like every kind of test or technique, it has its limitations. And so post-approval monitoring kind of provides this safety net to kind of make sure that those risk assessments are actually doing what we think they're doing. We think that it would be really important to have this kind of post-approval monitoring in the pesticide regulatory process as well.
Why do you do what you do? Why bees?
Great question. The question I ask myself is why pesticides? Bees is easy. I love bees. And I always have. I grew up the son of two botanists. So that's to say around a lot of plants and a lot of different kinds of plants. And I just grew up kind of watching what visited them. And I then developed this like ecological fascination in mutualisms. And I, have an appreciation for farmers and agriculture. And so studying bees and pollination services kind of just was a perfect confluence of all of that. But studying bees is also really fun they're just such a great organism, variety of reasons, right? Bees are these flagship species. They evoke public support. That's really helpful when kind of communicating your research and getting on podcasts like this. But they're also these umbrella species, right? They have conservation needs that incidentally overlap with other taxa. They're indicator species, right? So they're sensitive to change and degradation. This is really important for my work, right? Bees are pretty sensitive to pesticide effects, and they also kind of experience the landscape at relatively large spatial scales, unlike some other invertebrates. And then bees are classically these keystone species, right? They have a ecological impact through their pollination services that is oftentimes disproportionate to their abundance. But so that's all like why I study bees. And like I said, the question I ask myself is why pesticides? It can be kind of rather dreary research, but I study pesticides simply because I care deeply about bees and other plants and animals. And I want to make sure that they persist for generations to come. The plants and animals. Pesticides, we could do better with.
I love Charlie's thoughtfulness in his approach to research and the work that still needs to be done when looking at the quite often devastating effect pesticides can have on bees. The evidence is clear. Our current regulatory systems are falling short in protecting native bees from the unintended consequences of pesticide use. It's a call to action for more rigorous post-approval monitoring of pesticides. Thanks so much to Charlie for sharing the study and clearly explaining the consequences of understudied and underregulated pesticides. And thank you for joining us. Please take a moment now to visit our website, thebeesknees.website, and sign up for The Hive, our twice-a-month newsletter. Also, check out episodes 19 and 20, which look at the dangers of insecticides on bees. Until next time, just say no to pesticides.